Okay, as promised, let's discuss these problems. I know I mentioned in the lecture that we'll be covering problem 34, problem 42, and problems 52 and 53. I already did in the lecture problem 56, so if you did not catch that, please review that so that we're all on the same page. Problem 53 is actually a data problem, so remember those things, okay? So they are not all completely off of the hook. I'm going to try to do this ones as fast as I can without having to lose any kind of details on it. So the last question of the day actually is to finish the calculation, especially the number-wise, okay? I'll try to get as much numbers as I need for my discussion, but you need to really finish these problems. So problem 34, it gives me the number of moles, n equals 2.35 mole, okay? And then of a diatomic ideal gas, so they tell us that basically diatomic, that means CV is already equal to 5 halves of an R, and CP is just add to it 2 basically, 2 more degrees of freedom, so that's going to be, add to it just, to call it the R, CP is equal to CV plus R, so it's going to end up with being 7 halves of an R, because they tell us in the problem that it's a diatomic gas. That's how we know these values. And they give us a PV diagram. So let me draw quickly the PV diagram. I'm going to be erasing because this is an eraser place that I can erase in. So please keep this data in your notes. So we go from point 1 in the PV diagram to point 2. Again, this is an engine on a constant volume. So this is an isochoric process. And then we go through process from 2 to 3 on an adiabat. So the process from here, so this is, by the way, there is another also isobaric process, but this process in here is Q equal to 0. That means it's an adiabat. So basically we start from 1, going to 2, going to 3, and back to 1. That is the cycle. And it's an engine, so actually the direction of it in here is clockwise, indicating that this is an engine, okay? If we went the opposite direction, that's going to be a refrigerator. Okay, this is 1 atmospheric value, so we know the lower pressure is 1 atmospheric value, and we know also this temperature being 300 Kelvin. So they were nice enough to give us these temperatures already in Kelvin. This is room temperature, about 25 degrees Celsius. T3, so this is T1. T3 was given to us equal to 492 Kelvin. And T2 was equal to, or is equal to 600 Kelvin. So from the get-go, had this been a Carnot cycle, we know its efficiency. It's not, okay? This is not a Carnot cycle. The equivalent, if we're going to do this one, it's the highest temperature 600, the lowest temperature 300. We don't care about the 492. That's in between. So what we say in this case is 300 over 600, which is 50% efficiency, because 300 over 600, that's 1/2 deducted flow. So this is at best as it's going to get had it been a Carnot cycle. It's going to operate at 50% efficiency, okay? But of course it's not, so it's going to be less than that. So we need to check that. So they didn't ask us to do that. Okay, so processes 1 and 2 are constant volume, 2 and 3 is an adiabatic process, and process 3 to 1 is at constant pressure at 1 atmosphere. The value of gamma, so since they said it's a diatomic gas, but they went ahead and gave us gamma anyway, 1.4, so we know what gamma is going to be in this case, okay? Now, so that's all of the information that was given to us in this problem. And we deduced already CV and CP from the information, the fact that this is a diatomic gas. And they want us, find the pressure and the volume at all points. Okay. Obviously, I'm going to use PV equal to nRT, by the way, for the most part. Okay. N is 0.35. R, it's 8.314 joules per Kelvin per mole. Okay. T is the temperature. I know what T1 is. It's 300. I know what the pressure, which is 1.01 times 10 to the power 5 Pascal. Okay, I convert it right away to Pascal. So I can find what this volume is right away. And since they asked us to question A is to find the pressure and volume. The pressure is given already for point A. All we needed really is to find the volume. So if we find the volume, we use the expression that the volume, V1, is equal to nRT1 over P1, and this will give me the volume. So if I plug in the numbers in here, N is 0.35. Let me get the calculator quickly. So 0.35 times 8.314 times the temperature, which is 300. The whole thing is divided by the pressure, which is 1.01. Let me put this in parentheses so that I don't have any surprises. Times 10 to the power 5. And the answer, of course, is going to be in cubic meters, okay, because everything is in SI. So it's going to be 0.0086, 0.00864. I have 3 sig figs cubic meter. Or, if you like, 8.64 liters. If I divide this by 1,000. Oh, I'm sorry, if I multiply it by 1,000. Okay? So that's in a nutshell what the answer is. So it's 8.64 liters. So that's how much volume V1 is. And that's, by the way, the volume V2 too. Since this is an isochoric process, so that's the volume. So all we need is to find the pressure P2. For the pressure P2, since now we have the volume, all we have to do is use nR T2 now divided by the same volume that we found from before, okay? Because it's the same process. So what we do in this case is P2, remember, is equal to nR T2 divided by volume V1, which is nR T1, and when I divide by P1, I take P1 to the numerator. Cancel the R's, cancel the N and R, so we don't care to input those numbers. T2 is 600 Kelvin, T1 is 300 Kelvin, so this is twice P1. So whatever was P1, this one is twice, so this is 2 atmospheric pressure, or 2.02 times 10 to the negative, 10 to the power, 10 to the positive 5 Pascal. So simple as that. So this is 2 atm. Okay, that's the answer to the second question. So we found the pressure there. Now there are several ways of getting this answer to 3. Either use PV equal to nRT, or use P to the power gamma here. No, P times T to the times V to the power gamma here, and gamma is 1.4, equals to the pressure in here, which is given. This is 1 atmosphere, this is 2, times V to the power gamma, and you can find what that volume is. Or use PV equal to nRT and compare it to this one. So we're going to use PV equal to nRT because I don't really want to do the powers. So this point in here, we have the atmospheric pressure and we have the temperature. So we know that P3, V3, that's what we want to find, is V3, by the way. And P3 is the same as P1, by the way, same as that pressure in here, is equal to nR T3, okay? And P3, okay, let's erase this thing in here quickly here. So what that means is that V3 is equal to nR T3 divided by P3, which is P1. And P1 from this expression is equal to nRT1 over V1. So this is nRT1 over V1. So I'm going to put V1 in here in the numerator. So again, cancel the nRs in here. And this is T3 over T1, which is 492 divided by 300. So the volume V3 is 492 over 300 times the volume that we found earlier, which is 8.64 liters. So that's the algebra for this one, this requires a calculator, so it's not hard to find. So it's 492 times the volume, which is 8.64, divided by 300. Of course, it's going to be more, of course. The volume is 14 liters. Wow. 14.2 liters. Okay. So this is 14.2 liters. And thus, you can see from this graph in here that this volume is much higher than this volume, and that's basically understandable. Your task is to check this number, okay? And check it, use the other relationship, PV to the power gamma. I know that P2, V2 to the power gamma is equal to P3, V3 to the power gamma. Remember, this is an adiabatic process going from 2 to 3. That's why this relationship is true. I have P2, I have V2, but use the correct, you don't care about the conversion here. You can use the liters, is fine. The point being in here is that this relationship should be true. So that's how you check your answer, you know. That's how you sometimes do this thing. So we found all of these answers in here. So let me erase this stuff in here since I don't need it. So basically we found all of this stuff, okay? 8.6 liters, the other one is 14 liters, the second pressure was, so we have all of these things in here. So the volume in here, 8.64, and this is 14. I'm using the liters, okay? And so on and so forth, okay? What was the next question? Find the net work, that's two separate words, okay, done by the gas in the cycle. The net work is going to be the entire area that is here, okay, in this case. So we can find this work in here. We can find this work is 0. From 1 to 2, the work is 0. Okay, it's easy to find. This work in here is just the difference in volume, picture it's in cubic meter, times 1 atmosphere. It's this area really, okay? So the work is going to be simply the work of the adiabatic process plus basically, or subtracted from it. It's going to be a negative value so that you're keeping track of this one. So the work of the adiabatic process, which is negative, plus the work in here, which is compressing the gas down to it, which is going to be simply equal to Cp. I'm sorry, it's equal to the pressure. Remember, the work has a negative sign on it. So it's going to be negative the pressure, which is 1 atmosphere, times the final volume, which is 8.64 times 10 to the negative 3, minus 14 point something, 14 point what? Forgot the number already. 14.2. The whole thing is, of course, I have the pressure in here, 1.01, 10 to the power 4, and here 10 to the negative 3. So that is going to be negative times the negative, which is going to be a positive number. So let's put that number in there since it's probably important to get it. So what I have in here is I have 1.01 times 10 to the power 5. I am going to arrange just a 2 because I have already negative 3 and a negative 5 in here, times the difference in volumes, which is going to be basically the 14.2 and the 8.64. I already made the conversions, okay? We take care of these things. So it's going to be 560 something joules, 562 joules. So plus 562 joules. Okay, the other one is going to be a negative number. This one in here in the adiabatic process is going to be a negative number. Please refer to the expression that we found in the lecture and finish it, okay? Finish this work in here. Remember, you're supposed to integrate from volume in point 2 to the volume in point 3 of minus, of course, P, which is given by a constant, which is P2 V2 to the power gamma divided by the volume to the power gamma times dV, okay? So you're going to drop a minus gamma to the power of minus gamma minus 1, and then you have the same constant P2 V2 to the power gamma, which is just a constant in this case, times the V to the power gamma minus 1 evaluates between the two limits, V1 and V2. Okay, plug in the numbers, and it's actually going to be related to the difference in temperature between the 600 Kelvin and the 492 Kelvin. So I hope that you guys can finish this part. Once we find this number, it's going to be a negative number. We plug it in here and we add the two, and we have the network. Okay, and find the net heat flow into the engine. Okay, for the heat, let me get a colored thing in here. For the heat, I have to be careful in here because there is a place where I actually have heat being added to the gas, and there is a time when heat is actually subtracted from the gas. So, and the question is the net heat. We can find one and we'll find the other, okay? So the question is, what is the question again? Is to find the net heat flow into the engine of the cycle. Okay, we have no heat in here. That's good. From 2 to 3. We have heat that is being added. We're going from 300 Kelvin to 600 Kelvin in a pressure cooker, basically, where the volume doesn't change. So in this case, there is heat that is added, and that heat is equal to Q added, which is QH in this case, is going to be equal to N times CV times delta T, which is just 600 minus 300 Kelvin. Okay, CV is equal to 5/2 of an R. Okay, during this cycle, we're dumping heat when we're cooling down from 492 Kelvin down to 300 Kelvin at constant pressure there. Okay, well then in this case, QC actually is going to be a negative number. In this case, it's going to be NCP, where CP is given by that number. Okay, it's given by this one. And times the final temperature, which is 300 Kelvin minus 492 Kelvin. Okay, obviously this number is negative, and that's why I put it QC. So we have a QH in here, we have QC in here. All you have to do is just plug in these things, and you're going to get your answer. So the first one, this one, is going to be 0.35. So let me finish these numbers quickly in here on a calculator, of course. So 0.35, that's the number of moles, times CV, which is 3 over 2. No, 5 over 2. This is the diatomic gas. 5 over 2 times 8.314. Never forget that because it's critical for the calculations. 600 minus 300 is just 300. Okay, so it gave me 2,182 joules, or 2,180 joules. Remember the sig figs. So that is QH. How about QC? Again, QC, it's a different calculation. It's going to be a negative number. So what I have in here is, again, 0.35 times 7 over 2 times R, which is 8.314, times the difference in temperature, which is negative 192. It gave me a negative 1,956, 1,955. Okay, let me round it to this much for right now. I think we only are supposed to carry 3 sig figs. That's fine. So this is basically QC in this case. Okay, that is the amount. So if you ask me how much the network that you should find in here, it's just the sum of these two algebraic numbers. So I could add these two numbers and tell you exactly how much you're going to find. And that is per the first law of thermodynamics, because the first law of thermodynamics says that if I start from any point in here, let's 1, go back to 2, and come to 3, if I start here, and go there, and come back in here, and close the cycle, delta U is equal to 0. And delta U is the sum of these heats, which is positive 2,180 minus 195, 1,960, or 1,900. So let me do the math in here. Okay, so it's going to be 2,180 Oh, I'm not typing, sorry. 2180 minus 1960. So I'm gonna roughly, okay, about 220 joules, okay? So give or take a few joules in here, okay, when you fix this this relationship. Plus W. So this must be 0. So the net work in here that you're going to find is around minus 220 joules. So this number in here that I was talking about in here should be roughly about negative 220 joules, okay? So I'm hoping that you guys would take that calculation and check my numbers, okay? So we found that answer to that question. How are we doing on time? Oh man, 20 minutes already. And then, what is the thermal efficiency of the engine? So what is E? Okay, so we know what QH is, 2180. We don't care about QC when we're doing the efficiency. We know what the W is. So all we have to do is now find the efficiency. And as I was saying, this should be less than 50%. If we find it more than 50%, we have a problem before us, okay? So let's find the efficiency of this engine and see if it is indeed less than that. So E is equal to 220 joules. That's the work that we're getting from it, divided by 2180 joules. That is clearly less than 50% efficiency. It's clearly less than Carnot engine, okay? So this is going to be basically what? 220 divided by 2180, and that is a 10% efficiency. Versus a 50% efficiency had it been a Carnot cycle. Okay? So that is basically the idea behind this problem. Okay, problem 42. Problem 42 gives me a different cycle, and it gives me a monoatomic gas. Okay, so we know for a monoatomic gas, CV is equal to 3/2 R and CP is equal to 5/2 of an R. Okay, that's known. And it tells me that the path of the, and it goes around this cycle, and it shows you the cycle. So let me draw the cycle quickly here. So what I have in this cycle, I have point A, point B, and point C, okay? And it is really an isobaric process, an isochoric process, and a process that doesn't have a name, which is really a straight line in here. So we're going through this cycle in here. This is point A, this is point B, and this is point C. The volume in points B and C is equal to 0.8 cubic meters. The volume in point A is equal to 0.5 cubic meters. The pressure in point C is equal to 1 atmospheric pressure, basically, 10 to the power 5 Pascal. And the pressure in point A is 3 as much, which is the same pressure at point B, which is 3 times 10 to the power 5 Pascal. Okay, so we have all of the information now. So the cycle C to A is just a straight line. They tell you that, okay? Okay. The path process for CA is straight line in the PV diagram. Calculate Q, W, and delta U, and so on and so forth. Okay, from here I can tell you exactly what the W is, because W is this area with a negative sign in this case, because we're going clockwise. So this is what W net is. It's equal to 1/2 with a negative sign, okay, times the, this is a triangle. What's the area of a triangle? It's the height times the width times height divided by 2. So the width is just 0.8 minus 0.5, which is 0.3. And the height is equal to 3 minus 1, which is just 2, times 10 to the power 5. So the work is in here, 2 cancels 2, is 0.3 times 10 to the power 5 joules. So that is the net work. So we know exactly how much net work this thing is, just by looking at the graph in here, because this is a simple shape. I can find its area. I don't have to integrate anything and anything. So calculate Q, W, and delta U for each of the processes, though. Okay. Let me get another pen in here. Well, W is equal to 0 here. Okay? We need to find W here and Q there. And delta U, which is just the sum of these two numbers. So W in that from A to B, W is equal to minus the pressure, which is 3 times 10 to the power 5 Pascal, times the final volume, which is VB, minus the initial volume, which is VA. So this is equal to minus 3 times 10 to the power 5, 0.8 minus 0.5, which is 0.3. So this is minus 9 times 10 to the power 5. Sorry, is it 0.9? 0.9, yes. Times 10 to the power 5 joules. That's simple as that, okay? So that's how much work in that section. How much heat in that section? I'm still doing A to B. Well, that is going to be equal to NCP times delta T. I don't have delta T in here. You're saying, well, we can find it. We have the volume and the pressure in that point. So technically, we know what TA is. TA is simply PA VA divided by NR. Did they give us what the number of moles in here? They did not give us what the number of moles in this case in here. A monoatomic ideal gas is taken around the cycle and shown in the direction shown, the path for the process CA, and the P we calculate delta U. Okay, let's see here. Maybe we can find it in a different way. We know what TB is. TB is the same thing. PB VB over NR, correct? So that is basically, the number of mole will cancel in here from this expression. Okay, because once I find delta T, which is just basically divided by NR times, the pressure is the same, by the way. PB is the same as PA, which is P. So it's going to be P times, I'm calculating the delta T only, okay, which is VB minus VA. You see here, there is something that was not given, and you would be tempted to think, there is something I can't really find anything. But you can, because the N will cancel, because this N times Cp, N times Cp, remember Cp is equal to, is this a monoatomic gas? Yes, it's equal to 5 halves of an R times delta T, and delta T is this whole thing, the pressure times VB minus VA divided by NR. The N and the R cancel, and this expression is just 5 halves times the pressure times the difference in volume. Hey, the pressure times the difference in volumes is just the work with a negative sign. So whatever we found in here, we change its sign and multiply it by 5 over 2. That's it. So the answer is going to be 5 over 2 times 0.9 times 10 to the power 5. So the answer is going to be, hold on, let me do that math quickly here, 5 over 2 times 0.9. 2.25. So the Q here is 2.25, 10 to the power 5 joules. Okay, I took advantage of this expression in here. Let me explain. This Q is 2.25 times 10 to the power 5. The reason is because P times VA is the same, or P times the difference in volumes is the same expression for the work. The work had a negative sign by definition. By the way, the book uses for the delta U, Q minus W, where W is defined as the integral of PdV. And that is really defies common sense. This is the definition I'm using, which is used in all thermodynamic books. So the minus in here and this would be just the sum of the two. If the work turned out to be negative, that means it's energy taken from the system, and the reference in this case is the system itself. So it's negative. This means the system is doing work and losing energy in the process. So it must come from somewhere. That's my convention. That's the one I'm sticking to. So hopefully you guys are not confused. Please, if you do, there is an issue, please let me know. Anyway, so we can find for this process how much delta U. Delta U for this section is just add the two numbers. So delta U for this entire, we're still doing the cycle, the process AB. So delta U, just add these two numbers, 2.25, 10 to the power 5 joules. And then you have minus 0.9 times 10 to the power 5 joules. And 2.25 minus 0.9, what is that number again? Oh man, I don't feel like doing the mental math. 2.25 minus 0.9. So it's going to be 1.35 positive 1.35 10 to the power 5 joules. It has to be positive. The reason why it has to be positive, because the temperature went up. So this isothermal in here is lower than this isothermal. Since there is an increase in temperature, definitely the entire energy of the system must have increased through this process only. Okay, so we have some numbers. Hopefully I have them saved in the calculator of the computer, so hopefully you guys have them noted. Okay, from the process BC. The process BC is easy, as I said, W is equal to 0. So all we have to do is find Q in that section, okay? Q in that section. So Q, for now we're doing BC. Q is equal to NCV delta T, okay? Well, we don't have the T's. Again, we're going to use advantage because we don't have the number of moles also, okay? So we can't really know the temperatures, but we know roughly how much this expression, again, using the same trick as we did before. CV, by the way, is equal to 3/2 now of an R, because this is a monoatomic gas, 3/2 of an R. And this point TC and and VC, we have them according to this expression as follows. Again, P B times VB equal to NR TB. And then I know that PC, VC and VB are the same thing. These two volumes, VC and VB, are the same. So these two numbers are identical, equal to NR TC. So I'm looking at TB minus TC, or TC minus TB. That's what the delta T is. Delta T is simply TC minus TB. It's going to be a negative number, of course, because TC is less than TB. But the point in here is that delta T is equal to, I'm dividing by NR, I'm dividing by NR, and I'm taking V and B or VC the same out, which is 0.8 cubic meters. So it's going to be VC divided by NR times PC minus PB. Okay. Again, since I don't have N, the N cancels the N. As a matter of fact, also so is the R too. So we have Q in this cycle is equal to N times 3/2 of an R times delta T. And delta T is that you have VC, which is 0.8 cubic meters, divided by NR times PC minus PB. That's good, because then we have everything. N and R cancel with the N and R, and I have 3/2. Okay, I know what PC is. It's 1 atmospheric pressure, or 10 to the power 5. The other one is 3 times 10 to the negative 5. So this difference is 2 times 10 to the negative 5 with a negative sign, and times VC, which is 0.8 cubic meter. So it's minus 3 over 2 times 0.8 times the difference in pressures, which is just 2 times 10 to the power 5. I already took care of the negative sign outside, okay? So let's get this number. 0.8 divided by 2 is 0.4, or 2 times 2 is gone already. So I think we can do this one easily. 0.8 times 3 is 2.4 with a negative sign. So it's a negative 2.4 times 10 to the power 5 joules. So that's how much heat was dumped from B to C, okay? The question is, so how much delta U in this case is exactly Q, is exactly minus 2.4 times 10 to the power 5 joules, correct? Because W is equal to 0 in this entire process. In the process going from C, by the way, in the lab, you will have a bunch of cycles like this one. Each one of you guys will end up, each group basically will end up working on 2 different engines like this one and answering all kinds of questions related to these engines. Okay, so it's similar to the lab. And the lab will give you far more practice than this one. Anyway, the process C to A. Now that we have to do some work in here. Look, I need to find W for this process, okay? And then once I have the W for this process, I can find, first of all, how much is delta U net so far, okay, between process 1 and 2, between this one and that one. I already found one that is negative 2.4 and one that was a positive, let me find the calculator. What was the number? Positive 1.35, okay? So I know delta U up to this point, it's a negative 2.4 and a positive 1.35 times 10 to the power 5. Okay, I'm not writing the 10 to the power 5 for right now. So it's a negative 2.4 and positive 1.35. So it's a negative, so far, 1.05 times 10 to the power 5 joules, correct? Now I know the entire delta U is 0, going from 1 back to 1. From A back to A is 0. So if this up to here, from 1 to C, from A to C, we are at a negative 1.05 joules, from here to back to C, it must be the positive 1.5 joules. So this must be 1.05 joules. If I can find W, then I can find Q. For this portion only because Q will simply be delta U minus W. Okay, so if I can find W, and W is just this area, okay, which is easy. I have the area of this rectangle, 0.8 minus 0.5, so it's 0.8 minus 0.5, times the height, which is just 1, which is 10 to the power 5, plus the area of this triangle, which I already found it to be the same thing as the area of the other triangle that I found earlier. This one is plus 0.3 times 10 to the power 5 joules. I'm sorry, that's the whole multiplication. I have to be careful in here. That's multiplied by 0.3 already. So this area is equal to 1/2 times the height in this case, which is 2, times this height, which is 2, times the width, which is here, which is the same thing in here, times 10 to the power 5, I'm sorry. Okay, cancel that. So it's going to be 0.3 times 1 plus 1, that's 2. So it's going to be 0.6 times 10 to the power 5 joules. So that's the work. And it's going to be this work in the bottom, but I'm interested in this part of the work in here. So, and this work is going to be a positive work as I am writing it. The reason why it's positive is because I'm compressing the gas from 0.8 down to 0.3. So the sign is correct, okay? And I need to find the Q now. The Q, I argued, it has to be a positive value for the delta U, 1.05 10 to the power 5, minus, did I put the joule here? 10 to the power 5, don't forget 10 to the power 5 joules, minus 0.6 10 to the power 5 joules. So the net heat in this one actually is gained, and it's going to be 1.05 minus 0.6, it's 0.5 minus 0.5, which is 0.45, 10 to the power 5 joules, okay? So that is the Q in this section, okay? So we found the Q, and we found the W, and we found the delta U, and everything. What are Q, W, and delta U for the complete cycle? The complete cycle, delta U is 0. So the last question, delta U is 0. Always delta U is 0 in a complete cycle, okay? What is the, and W is just add, W is 30.30, 0.300, or depending on how many sig figs in this problem. I don't know. 0.3 times 10 to the power 5 joules, or 3 times 10 to the power 4 joules. That's how much W. So how much Q must be? It's just 0 minus this number, so it's going to be minus 3 times 10 to the power 4. Verify by actually adding the actual Q's that we found. Okay, it should be the same number. Okay, I'm using just the first one. What is the efficiency of this engine? E. We can't really compare it to a Carnot cycle because we really don't have the temperatures and so on and so forth. Okay, we can express them in what we have, but at this point, what is E? E is going to be the work, which is 0.3, divided by the heat, which I did not calculate. Okay, remember, let me go back into the calculator. There was one of them 1.35, and okay, I think that's the only, no, there was actually, so we lost heat negative 0.4, but we added another one, I think. We have 1.35 for this cycle in here, if I remember the numbers. Please check these numbers in here. But we just found another one in here for this portion, which was, how much was it? Because this one was negative in here, so we know that is going to be negative, which is the negative 1.05 10 to the power 5. Okay, 10 times 10 to the power 5 in here. But there was another heat in here that we found, and that heat, I forgot the number in here, need to be added to this one, and we divide 0.3 times 10 to the power 5 by it. Okay, so you can finish this one in here. If you have difficulty with it, please let me know. It's already running into 40 minutes. Okay, let's quickly do the other two problems. Problem 52 and problem, the last one, okay, 53. Problem 52, basically what it says in here, it says you have 250 cubic centimeters to make coffee. So that's how much water you have. 250 cubic centimeters of, we need the mass of the water in grams. So the mass of the water is rho times the volume, and rho for water is 1 gram per cubic centimeter. So we really have 250 grams. Okay, the density for water is 1 gram per cubic centimeter, and since you have 250 cubic centimeters, you have 250 grams, or 0.25 kilograms. Okay, so whichever one you use, it's up to you. To make coffee, you place an electric element in the cup as the water temperature increases from 20 degrees to 78 degrees. So we know what the temperature is. So it was T1 is equal to 20 degrees Celsius. You have to be careful with these temperatures, because if you're going to be calculating entropies, you're not going to be using these numbers in here. You're going to use use them in Kelvin. Okay, 78 degrees Celsius. The temperature of the heating element remains at 120 degrees Celsius. So the element that you use to heat the water with, its temperature of the element is equal to 120 degrees Celsius. So it doesn't change because it's plugged into the power. So this is an isothermal process for the element itself, but the water is not. It was at room temperature, and now it's very hot. Okay. Calculate the change in entropy of the water. So for the water, we did that in lecture, and we found that the change in entropy is equal to MC ln of T final divided by T initial, and this will be an increase in entropy. The mass of the C, by the way, for the specific heat for the water is 4,184 or 90 or something like that joules per kilogram per Kelvin, okay, or per degree Celsius, same thing in here because you're doing the difference in temperatures. Okay, so we have that. We have the mass, which is 0.2, and we have the temperature. So all I'm going to do is multiply 0.25 times this number, 4,190, times the ln of, again, 273 plus 20, that's 293, and 273 plus 98 is 273 plus 78, I'm sorry, is going to be 351. So basically, this is the expression that you're going to find the change for the water. It's going to be a positive number. Okay, so and the change for the entropy for the part B, where is it, part B? the heating element C. For the heating element C, it happened at constant temperature. So all I'm going to do now is finding the, did they give us the enthalpy of this element or anything like that? No. To make coffee, you place a heating element in the cup. As the water increases, the temperature of the heating element. So basically it's the water, because the water now will receive heat. So how much heat the water has received? It's going to be just delta Q, which is simply equal to mass of the water times the specific heat times the change in temperature, which is 78 minus 20 degrees. Okay, M is given 0.25 times 4,190 times 78 minus 20, that's 58. Now if I multiply these numbers, that's how much heat we received in the process. So that's how much heat we got from the heating element, because that's what went out to heat so we got 60,000 joules, basically 60,755 joules. Now this one went to heat the water, but where did it come from? It must have come from the element itself. So the element entropy, delta S, ds, is equal to minus, the reason why I'm putting a minus is because it lost this heat, okay? 60,755 divided by, it happened at constant temperature. So when I integrate ds over t comes out of the integral, it's just integrate dq over t, dq says just this amount. That's how much heat lost by the element divided by the temperature, and temperature 120 Kelvin, 120 degrees Celsius, which is 120 plus 273. So it's going to be this number divided by that, and I'm fine with it too. So it's this number, the one that we found earlier, divided by 120 plus 273. So it's going to be 155, basically, with a negative sign, 155 joules per Kelvin. That's how much entropy was lost by the element in here. How much entropy gained in here, we really need to find the other one. So this is the element. We need to find that of the water to compare the two. So we really have to use that formula in there. So let me do that since I didn't do it. So I have 0.25 times 4,190 times ln, open parentheses, of 351 divided by 293, and that's going to give me 189.2, or so this delta S in here is 189 joules per Kelvin. So that of the universe for the entire process, I think that's the next question, for the entire entropy of the universe when we heated the water to make coffee, is basically this number, which is a positive number, plus the other number, which is a negative number. So 189 minus 155, and that is going to be a positive number per the second law. That's critical, okay, that the second law was not violated in this process, okay? So we have the first one, the last one, minus the first one. Come on. I'm just copying the number. So it's giving me 34.6 joules per Kelvin. That's how much the entropy of the universe have been impacted. In other words, the entropy of the universe went up. So the last problem that I want to discuss, of course, let me clear out this thing in here, is problem 53, and it's all data problems. So I'm going to just start it probably because it's an easy problem to do. So they gave us problem 53, 4 systems, okay, 4 engines. And they gave us the TC and the TH of each and every one of them, and they told us how much they're, so I'm doing the last one. So the first engine, engine A, operates between 47 degrees Celsius and 177 degrees Celsius, and its efficiency is claimed to be 21%. And the second engine operates between 70 degrees Kelvin, 70 degrees Celsius, and 197 degrees Celsius, and its efficiency is 35%. And the fourth engine operates between negative 33 degree Celsius and 247 degrees Celsius. Okay, and so all of these temperatures are in degrees Celsius, not in Kelvin, which is very important that you have to convert them into kelvins if you're going to do anything with them involving efficiencies. So this is a 56% efficient, so that's very high. So hopefully it's going to be okay. 37 degrees Celsius for the last one, 137 degrees Celsius, and its efficiency is 20%. Okay, so the first question is, based on TC and TH values for each prototype, find the maximum possible efficiency. Basically find their ECs. Okay, remember EC is 1 minus TC over TH, except that this TC and this TH are written in Kelvin. So for example, for the first one is equal to 1 minus 273 plus 47 divided by 273 plus 77. Okay, 177 that is. And this efficiency, of course, is a ceiling, how much maximum efficiency you're going to get. Okay, this is the top. You cannot reach if the efficiency that the person is claiming is more than this, then that thing is wrong, whatever they did. So there is a scenario behind this data that they give you. So 1 minus, open parentheses, 273 plus 47 divided by, open parentheses, 273 plus 177. So they're saying this is 28.9% efficient. Had it been a Carnot cycle, and the people are claiming to be only 21% efficient, which is fine, which is less than 28.9, 29% basically efficiency. Okay, the second one, which is operating between these two, the other two different temperatures. Let me go back into the same formula basically and change the numbers in it. So the lowest temperature is 17 degrees and the highest temperature is 197 degrees. Okay. And that is a 38.3%. So this engine is 38.3%, and they're claiming it to be 35%. Okay. Well, they're right. At least potentially they are right. Okay, because their efficiency is less than that of a Carnot cycle. Let's check the third one in here. The third one is operating between the temperatures negative. So when I subtract the negative, I add. Oh man, when I do that, so I have to be careful in here. I have to really subtract the 33 degrees, and the highest temperature is 247 degrees. So I'm going to add the 247. Okay. And this is a 53.8 efficiency. Had it been a Carnot cycle, they're claiming it to be 56%. That is nonsense. That is incorrect. That violates the second law of thermodynamics. So this data is no good. So the third data in here that you look at it is no good, because the efficiency, had it been a Carnot cycle, is less than 54%, and they're claiming it to be 56% efficient. So this is no good. No es bueno. The last one of the thing in here, so let me plug in the numbers since we are almost done with this, is to basically we have it operating between 37 degrees and 137 degrees. And the efficiency of that one is 24.4%. Okay, so that's how, is that acceptable? Yeah, it's 20% is less than 24.4%. So that answers the question. So the question is, based on this one, plug in all the values of TC and Winston's reduction. The second question, are any of these claims in efficiency impossible? Yes, claim 3 is impossible because it violates the second law of thermodynamics, because it's going to invent an engine that is more efficient than Carnot engine, which is not possible, which is in violation of the second law of thermodynamics, as we showed in lecture. For all prototypes with an efficiency that is possible, rank the prototypes in decreasing order of the ratio of claimed of efficiency versus that to a maximum. All you have to do for that is take this number and take it divided by this one and find how far they are from being the Carnot cycle. Take this one in here and divide it by that one, and you'll find how far they are. Take this one and divide it by that one and find how far they are. This you cannot use. It's going to give me nonsense. And you're going to find from the ones that is very close from being a Carnot engine to the one that is not so close, like a Stirling engine that we did in lecture, is actually very close from being a Carnot cycle, except that it's very hard to build engines based on it. Okay, it's very hard to master its technology. Maybe you do it and you will revolutionize the building of cars. Okay, so these are 4 problems. I know it took almost an hour, but hopefully you benefit from it. This is also a review for your exams, okay? Don't forget that part of your task for this portion is to verify all of my numbers and make sure that I am correct on that and finish the calculations whenever it's needed, okay? Thank you.